anyone has a question on any of the problems we did in class last time, or any homework questions, we could go over those. If not, we'll just get started on this last slide of trig sub. These things take a lot of practice because they're very involved in getting from point A to point B, from the beginning to the end of these. So let's go ahead and notice that our denominator here is a trinomial. There's three terms. And what we've seen when we have a trinomial in the denominator is that we have to complete the square so that we can turn it into a two-termed expression. So anytime we have a trinomial in the denominator, we almost always go to complete the square and factor the thing. So let's go ahead and do that first. We're going to look at this coefficient right here. And to complete the square, we divide it in two, and then square that result. So if we take that -6, divide it by 2, we get a 3, -3, and then we square it, we get a 9. So we need a constant of 9 in order to complete the square. So what we sort of think about doing is grabbing 9 out of that 34. So we can say this. We could say, okay, let's take 9 from the 34, and that's going to leave a 25. This now here is a perfect square trinomial that is factorable. So that puts us in this situation where we have dx in the numerator, and we have an x minus 3 quantity squared plus 25. So now we should start thinking trigonometric substitution because we see a sum of squares. Whenever we see a sum of squares or a difference of squares, that's kind of the hallmark, the red flag for trigonometric substitution. And the strategy we've been using in here is to create a sum or difference of squares where the constant is a 1. Right now the constant is a 25, so we want to factor that 25 out so that we can have a sum of squares with a 1. Okay, that 25 is in the denominator, so we're going to pull that out in the denominator. And in the denominator we now have, let's think about this very first term. This first term here, this has no 25 in it. So when we start to factor out that 25, if there's no 25 in it, it introduces a 25 into the denominator. Or you could go ahead and proactively put it, sort of like that, a 25 over 25, and you're thinking about factoring out that 25. Now there's no power on it. A lot of times we've been pulling these constants through a square root or with a power of 2 or whatever. There's no power there, so it comes out as a 25. And when we think about this first term now, we want it to be a square. It's not written as a square right here, x minus 3 squared over 25. So we want to write it as a square, so we do that. Now we have a sum of squares with a 1. That's our target setup to use trigonometric substitution. There is a shortcut on this one does anyone see the shortcut? If no one sees it, that's fine. Let's go through it with trigonometric substitution, and I'll point out what will happen when you don't see the shortcut. Exactly, that's the shortcut. It's already in inverse tangent form. Remember that our basic inverse tangent is that the integral of dx over x squared plus 1, that is arctangent of x plus c. So that's already actually in that form, so we could immediately write down the antiderivative in conjunction with reverse chain rule. We could take the derivative of the inside here and divide and get the coefficient. What is the derivative of the inside here?
1/5.
1/5. 1/5 is the derivative in there, because this is 1/5 x minus 3/5, right? 1/5 x minus 3/5. So the derivative would be 1/5 if we took the derivative of the inside. But let's pretend that we didn't notice that, oh gosh, we're already in inverse tangent form. Let's just blindly say, hey, trig sub, we see a sum of squares. Sum of squares, trig sub, and sine, secant, or tangent for this sum of squares?
Tangent.
Tangent. Anytime we have a plus is like a t, we're going to use tangent. So we're going to say x minus 3 over 5 is equal to tan of theta. And then we take the derivative of both sides. And once again, the derivative of the left is 1/5. We need to put a dx in there. Let's see if my scribble will work. So 1/5 dx, derivative of tan is secant squared of theta d theta. So that's where we're at. Now we're going to replace everything in the integral so that we turn everything into thetas. So we have 1/25 out in front. In the integral, let's see, the dx becomes 5 secant squared of theta, d theta. That's the numerator. Denominator is just tan squared plus 1. So tan squared plus 1.
Which is just secant squared.
Which is just secant squared. Make sure that identity, you've got to get that identity down pat. This picture is way helpful. There's your identity. So we end up with 1/5 integral. We'll write out this step here. So we end up with secant squared over secant squared. So we end up with 1/5 the integral of d theta. And that's the, oh gosh, if you get to the point where you're just integrating d theta, that means there was a shortcut that you just didn't see. Because watch what happens. When we integrate d theta, don't we just get theta? And if we come back up to our substitution step right there, how do we solve this for theta? What do we do?
Inverse tangent.
Inverse tangent. So if we want to solve this for theta right here, let's write it down here. Theta is inverse tangent. If we take the inverse tangent of both sides, there is theta. And so we get exactly what we would get if we would have noticed that you could integrate directly. So we're going to have 1/5 inverse tangent of x minus 3 over 5 plus c. So now let's confirm if we did recognize that we had a shortcut option, let's just confirm that we are getting the same thing. So let's see, it's at this stage right here where we could recognize that, oh gosh, it's in inverse tangent form. It's a sum of squares with no power, right? We've got a sum of squares with no power. If there was big parentheses and a power, a square root or a 3/2 or a 5/2 or whatever, then you would have to use trig sub. But because we have a sum of squares right here with no power on that denominator, you could just cut to the chase. You would say this, if we were cutting to the chase, we would say, okay, we have 1/25 on the outside times, this is an inverse tangent of whatever's in the parentheses, so inverse tangent of x minus 3 over 5. But then we have to do reverse chain rule.
And divide by 1/5.
Divide by 1/5, that's the reverse chain rule, plus c. And now dividing by a fifth is multiplying by 5. 5 over 25 is a fifth. And so, of course, we end up with the same answer. So you could ideally you start to see those three inverse trig antiderivatives, right away. But if you don't, if you know your basic trig sub, you can even forget about it because you get to the right answer anyway. So if you know trig sub, you don't even actually have to memorize those anymore. But this is obviously faster if you have that one memorized. But it will come out in the wash. So even less memory. So it's incredible. All right, any step there that feels less than incredible that you want to ask about? Okay. The easy section of chapter 8. PFD, partial fraction decomposition. Ooh, sounds scary. Partial fraction decomposition. Let me point out the sum of these two rational functions right here. You did this a boatload back in algebra where you took those two things, you got a common denominator, and you ended up with one rational expression. So you found a common denominator, you multiplied this one by x plus 4 over x plus 4, you multiplied this one by x minus 2 over x minus 2, got that common denominator, combined like terms in the numerator, and you got to that. Now you did that a ton. But you've never gone backwards. So partial fraction decomposition takes a more complicated rational function and breaks it into partial fractions. So we're going to call these partial fractions. We're taking this complicated fraction and breaking it apart into two smaller fractions, which are partial fractions. Integrating this is simple. Right? Both of those are natural logs. Right? The antiderivative for both of those is really easy to do. So right here, this antiderivative, this is going to be natural log, absolute value. Oops, I don't need the integral, I just integrated. So that we don't need. So we integrated. Right? As soon as we integrate, that integral symbol vanishes. This is in log form. The derivative of the bottom is the top. And here we can think of factoring out the 2, and then the derivative of the bottom is the top. So we would end up with 2 natural log absolute x plus 4 plus c. So that's really easy to integrate if you have these partial fractions. If you break it down into 2 little fractions, like that is kind of hard, right? We could complete the square and go down a very complicated inverse trig method, what we just did with trig sub. Complete the square and go. But this is going to be a much easier technique. And so then the question is, well, if I've got this trinomial in the denominator, how do I know whether I should complete the square and go down the trig sub method, like we just did earlier today? Or try to attempt PFD, partial fraction decomposition? Well, hopefully the answer is kind of obvious. If that can factor, then go PFD. If this factors, then go PFD. So does it factor? If it factors, if yes, then go to PFD. If no, go to trig sub. You're going to have to complete the square and end up doing trig sub. So if that denominator is a trinomial that factors, then PFD is the way to go. It's going to be way easier. So then the question becomes, all right, well, how do we take this rational expression, how do we take it and break it apart into its constituent partial fractions? How do we find those two partial fractions? Well, obviously, the denominators are coming from the factorization of this. Right? This factors into x plus 4. It's one of those things. factors into x plus 4 and x minus 2, right? And so you can see that the denominators are coming from those factors. And the math is going to be trying to find the numerators. So here's how we do it. So there are 3 techniques. Don't read that. That looks so bad. What you should be seeing here is that if you can factor your denominator into 2 factors, you will then have 2 fractions. So we're making it look a little more complicated than it is. They're generalizing. Sometimes generalizing makes things look really messy. But really, all they're saying is that what we're going to do is take our rational function, so our rational function, the numerator is p, the denominator is q, and we're going to factor q, and each of those denominators will create a partial fraction. All right, so here's what we do. And it's really back to algebra. So let's use the traditional partial fraction method. And then, let's see, on the next slide, we're going to do, oh, no, it's not the next slide. It's, I guess I can't remember how I organized it. Okay, yeah, we'll do them both here. So there's 2 techniques for this type of partial fraction decomposition. Let's do the traditional method first. So here's what the traditional method says. So it says, okay, we're going to take our fraction, our rational function, and we want to break it into 2 partial fractions. So the 2 partial fractions have this form of a constant divided by the denominator by that factor. So that's what we want. And now we just do basic algebra. We're going to clear out the fractions. So we're going to multiply both sides by this denominator on the left. So we're multiplying the entire equation by x minus 2 times x plus 6. So across the entire equation. So that's going to cancel with this denominator on the left. So we're just clearing the fractions. We're doing what we normally would do if we want to clear the fractions. When this distributes to the first fraction, there's one common factor that will cancel. So we're going to be left with a multiplied by x plus 6. The x minus 2's are canceling. So this whole quantity here, right, is being distributed to this fraction, to this fraction, and to this fraction. When it multiplies to this fraction, all you have left is the 8, because 2 factors cancel. Multiply by this one, the x minus 2's cancel. And now when we multiply by the last fraction, the x plus 6's cancel. So we have remaining, we have the b multiplied by x minus 2. So standard algebra technique to get rid of fractions. Just multiply by the least common denominator, and that will get rid of all the fractions. Now, here's what the traditional method says. It says, okay, expand everything. So we're just going to multiply everything out. So that we have that. Just multiplying that stuff out. And then let's pair some stuff off on the right. Let's pair some stuff off. I'm going to write this as a plus b times x. So I'm going to group the like terms. I'm grouping the 2 terms that have an x together and factoring out the x, and then I'm going to just sort of group together the 2 terms that don't have an x. And let me ask you a basic question. If you have, let's suppose you have this. Let's suppose you have 2x squared minus 3x plus 1. And let's suppose that's equal to ax squared plus bx plus c. Can you tell me what a is equal to? What does a have to be? 2. What does b have to be?
3.
Negative 3. What does c have to be?
1.
1. If you have 2 polynomials that are equal to each other, that can only happen if the corresponding coefficients are the same, right? If you have this polynomial equal to that polynomial, the only way that's possible, the only way those 2 things can in fact be equal is if this coefficient is equal to that coefficient, this coefficient is equal to that coefficient, and that constant is equal to that. Right? It's the only way they can be equal. The coefficient of x squareds have to match, coefficients of x have to match, and the constants have to match. That's what we have down here. We have a polynomial on the left and a polynomial on the right. What is the coefficient of x on the left? 0. This is 0x plus 8. So we do in fact have a polynomial on the left. So from this tells us the following. It gives us a system. It says, oh, the coefficient of x on the left is 0, therefore the coefficient of x on the right has to be 0. Well, the coefficient of x on the right is a plus b. The constant on the left is 8. That must match the constant on the right. The constant on the right is the part that has no x's. So that's 6a minus 2b. So that puts us back into college algebra land. We've got a system of two equations with two unknowns. You can use substitution, you can use elimination, doesn't matter. Whatever floats your boat. So if we wanted to use substitution, up here we could say that a is equal to negative b. Then we plug it into the lower equation. Let's go ahead and simplify the lower equation first, though, because we can divide out a 2. We see that there's a common factor of 2. So we have 4. We divide out the 2. We have 4 equals 3a minus b. And now we can plug in multiple different ways, actually, we can plug in. You could turn the a into a negative b, or you could turn the negative b into an a. Doesn't matter. Whatever you feel comfortable doing, does not matter. I'm just going to replace the negative b with a. So I have 4 equals 3a. Negative b is equal to a. So we have that. So we get 4a equals 4. So a is 1. So 4 equals 4a. And that will give us the a value of 1. So there we go. There's our first step. We've got first constant. And how do we get the second constant? Plug it in. We'll back substitute it into wherever you want. You can plug it in there. You can plug it in there. You can plug it in there. It does not matter. So if you plug it in right here, you're going to get that b is equal to negative 1. So now we have our two constants. Now we have two partial fractions, each of which is easily integrable. So we are now in this situation where we can take our original integral, and let's call it something. Call it omega maybe. Omega works. So the original integral, the original indefinite integral, can now be written as the integral of, we found a to be 1, so 1 over x minus 2, plus b, which is negative 1, so let's make that minus 1 over x plus 6 dx. And we have a pair of logs, right? Each of those is a log expression. This will be natural log absolute x minus 2 minus natural log absolute x plus 6, absolute value plus c. And those two logs can be combined into a single log. We know log properties. Say again?
Division?
By division, exactly. Right. We will divide them. So here, that would be our simplified answer. So PFD, it really is a lot easier than trigonometric substitution. You just have to refresh your basic algebra on multiplying by common denominators and solving systems of equations, but a lot faster. So this is the traditional approach. The traditional approach is using the fact right here that we have a polynomial set equal to another polynomial, and you just match the corresponding coefficients. That's the technique, traditional method. Let's go with this other mysterious method called the convenient value method. So the convenient value method either works but the convenient value method is super slick when your denominator is linears. So these factors are linears. Theoretically, you could have a denominator that's an irreducible quadratic, which we'll get to. But when these are linears, this convenient value method, we're going to see this is actually pretty darn slick. So let's get this out of the way. I don't know why I didn't give myself more space. So let's try it with the convenient value method. So convenient value method. So what we're going to do is we're going to back up right to here. So we're going to, no, I don't want that. Never mind. I want this line, the next line. So we're going to back, no, I want this line. Come on. This line, that line. The original, when we first cleared the fractions, this is the line I want. Right there. So, let's see, where's copy? So we want that line, and what we're going to do is the following. So this equation, where's my paste? That? Okay. So this equation right there. Traditional method, we distributed everything and created a polynomial on the right and matched it to the polynomial on the left. Here's the convenient value method. What we are saying here is that this equation, we are going to imagine this is true for every single x. So that equation, we're going to say, okay, that's true. It's an identity. It's true for every x. Well, if it's true for every x, in particular, it's true when x is 2 and when x is -6. So we're going to choose a couple of x values that will reduce this tremendously. So we're going to choose, if it's true for every x, in particular, it's true for these two. And let's see what happens when we plug those in. All right, if it's true for x equals 2, there's no x on the left. But if I plug in 2 on the right, I get 8a plus 0. We're plugging in a 2 for the x. Oh, a is 1. If it's true for -6, let's plug in -6 for all the x's that we see. There's no x on the left, so we have an 8. Plug in -6 for this x, 0. Plug in -6 there, we get -8b. Oh, b is -1. Done. So the convenient value method is super slick. We'll see that we would just teach this method if it would work every single time, but there are times where you need the traditional method. So we need to have that, but if you're dealing with linear factors in particular, the convenient value method is very fast. So there's the a equals 1 and the b equals -1. So it gets us back to the partial fractions really fast if you have that set up. Yeah?
So it would work, for instance, if you had 3 factors.
It'll work even with 3 factors.
It will work?
Yeah. If they're all linear, it works beautifully. It works.
And that's just because all linear
right,
equations don't have poles or asymptotes, right?
Yeah, so as soon as we get to this stage right here, that's just a linear equation.
Yeah.
So it's a line,
Yeah.
And
And
so-
so true for all x's.
right? True for all x. Yeah. It's very clever.
I got something.
Okay, so we'll see some limitations to it in a little bit, but for now, that method is super cool. All right, let's take a look at this one. So here, the first step is that we want to factor the denominator. So if we want to factor that denominator, it's pretty easy to factor this denominator. We just factor out the power of the x first, what's it called, the GCF, greatest common factor. So we end up with that. Well, it's not factored all the way yet. And there is a very important theorem called the fundamental theorem of algebra. The fundamental theorem of algebra says that a polynomial with integer coefficients can always be factored down to linear and irreducible quadratic factors. An irreducible quadratic factor is something like x squared plus 1. You'd need imaginary numbers to factor it. X squared plus 1, x squared plus 4. Can't factor those with real numbers. So the fundamental theorem says that if you're only allowing real numbers, you can always get down to linears and irreducible quadratics. This is not irreducible because we can keep factoring. So we keep going. It's not irreducible. If it was x squared plus 1, that's irreducible. X squared minus 1 is the difference of squares, and we know how a difference of squares factors. So we have that now. Okay, so now it's totally factored. We have 3 linear factors. 3 linear factors. Now we are going to go to the guts. We're going to go inside and we're going to say, okay, well, let's take this factored rational expression and we're going to turn it into partial fractions. So we've got it all factored. We want to turn it into partial fractions. There's going to be a constant over each factor. So there's going to be a constant. There's going to be a constant over x. There is going to be a constant over x minus 1. And there's going to be a constant over x plus 1. And then we're going to take the entire equation and multiply it by the denominator on the left. And when you multiply everything by that denominator, so it has to go to all 4 parts. It has to be multiplied to this, to this, to this, and to this. Distributed all the way across. On the left-hand side, we are left with 4x minus 2. On the right-hand side, when that clump of 3, those 3 factors jump over to the a fraction, the x's will cancel. Because remember, this thing is, you're thinking of that as over 1, right? These factors, they come into the numerator of each of those fractions. So the x's are going to cancel. And when the x's cancel, we're left with a multiplied by x minus 1, x plus 1. We don't want to multiply it out yet, though.
Oh.
Not yet. And then when we multiply it by the b fraction, x minus 1's cancel. So we get that. And then we multiply it by the third one, and we get cx times x minus 1. So here is our PFD equation. So this is our PFD equation. And this PFD equation is where we decide, should we go traditional or should we go convenient value? Because everything is linear, convenient value is going to work really well. So let's go with that. When we get to the irreducible quadratics, we have to go with traditional methods, so we'll get a lot of practice with it. So there's no harm in going with convenient values. So let's see, our convenient values. Guess, what's our first convenient value?
1.
1. Second one?
-1.
Third one?
0.
So yeah. So those are the convenient values. Those are the zeros of each factor. This factor has a 0 of 0. This factor has a 0 of 1. That factor has a 0 of -1. So each 0 is a convenient value. So now we plug in 1 for every x that we see. On the left, when we plug in a 1, we're going to get 4 minus 2. 4 minus 2 is 2. On the right, when we plug in a 1, gone. 1 minus 1 is 0. Plug in a 1 over here, gone. 1 minus 1 is 0. The only term that generates a non-zero is the middle term. So plugging in a 1 will give us b multiplied by 2. So it gives us 2b. And that tells us that b is 1. So very quick. Now we plug in -1 across the board, every x we see. Plug in -1 right there. -4 minus 2 is -6. plugging in -1 on the right-hand side. This term is gone, because -1 plus 1 is 0. This term is gone, -1 plus 1 is 0. Over here, -1. So we get -2 times -1, so that's +2 times c. So we get 2c, and that tells us that c is -3. Following the process here, now we're going to plug in 0 for all the x's that we see. On the right-hand side, when 0 is substituted in for that x, we get a -2. On the right, when we plug in 0, this term is gone, this term is gone. Plugging in 0 here, we'll get -a. And so now we have all three of our constants right there. So that's a lot faster. So if we were going to do the traditional method, we would have to do what Tanner had suggested and multiply this out to x squared minus 1, distribute the a, collect all the x squareds, collect all the x's, collect all the constants. It's a pretty long process. If you have all linears, convenient value is way slicker. Okay, so let's take our original integral. Bless you. We'll call it omega or call it whatever you want just so we can rewrite it in a convenient way. So let's see. So we're going to have that the original integral, omega, is now equal to the integral of a is 2. I think we have that over x. And the next one I think was x plus 1?
X minus 1.
X minus 1. Okay, so 1 over x minus 1 plus 1 over x minus 1. And then c was 3 over x plus 1. So there is our PFD. We now have our partial fraction decomposition completed. And we did that because now we can integrate easily. These are all logs. So the first one, 2 multiplied by natural log absolute x. The second one is just natural log of x minus 1. The third one, minus 3 times natural log absolute x plus 1 plus c. And we can definitely use log properties here. On the exam, if I want you to use log properties, I'll tell you. Sometimes the homework has you do it, sometimes it doesn't. Depends on the problem. If we wanted to do log properties here, remember that the coefficients, they have superpowers. They can fly up to the top. These coefficients fly up to the top. And so here's what it would look like if we combined all these logs into one. We would have natural log of. Addition turns into multiplication. So that's going to be x squared multiplied by x minus 1. And I put an extra, we don't need this absolute value right there. If we're going to put it on the outside, do that. That's the numerator.
Hey, it looks like the original denominator.
It's getting close to what we started with, right? And then minus, that's going to pop into the denominator, and we're going to put a cube on that power. So this is going to be natural log absolute value of x plus 1 quantity cubed plus c. And there's a couple things here. You could say, oh, the x squared can't be negative, so you could pull that out of the absolute value and have it on the outside. This 3 could be inside the absolute value or outside. It doesn't matter. Both are the same thing. A lot of times you don't need to simplify your logs, but if you did, we'll just do it just for practice. It's good to practice. Yeah.
So is the division outside the logs, or would you have the log of the two parts?
Thank you.
I was gonna
Thank
say,
you.
I-
Thank you.
It
Yeah.
looks weird.
Yeah, I put this fraction bar, I made that fraction bar way too big. Sorry. Thank you. It's turning into one log, right?
Yeah.
It's turning into one log.
That makes a lot more sense.
That makes a lot more sense. It's turning into one log because log of A minus log of B turns into one log. We have log of A minus log of B. That's going to be log of A over B. Yeah, it's turning into one log, not two logs. One log's enough. Yeah, thank you for pointing that out. So the x squared, if we wanted, we could just move these absolute values just onto the x minus 1, because that's non-negative. All right, so we'll slowly ratchet up the complexity of the denominators. So right now our denominators have all been linear factors, and they've all been raised to the first power. So the next level of complexity, what if we have a repeated linear factor? So what if we had x minus 1 quantity squared? So a repeated linear factor. So the multiplicity of the 0 is going up. So remember the multiplicity thing? If you have x minus 1 quantity squared, the 0 is 1. It's got a multiplicity of 2, which if you're corresponding to graphs with polynomials would be a touch instead of a cross. Right? Odd multiplicity goes through the x-axis. Even multiplicity just bounces. Okay, so looking at this first example here, we see that we have a repeated 0. So this is already factored for us. We have a factor of x minus 6, and we have a repeated factor of x plus 2. So with repeated factors, our strategy is that for each repeated factor, we need to have a partial fraction for every power. So if we have x minus r to the 3, we'd have to have an x minus r fraction, an x minus r squared fraction, and an x minus r cubed fraction. So we're going to have a partial fraction for each power of a repeated 0. So down here, this tells us that we are going to have 16 over x squared, 16 over x squared so x plus 2 squared. This is going to be what the setup is going to be. We're going to have an a divided by x minus 6. Then we have our repeated factor. So we're going to have a b over that factor to the 1. But then we're going to have another partial fraction where that factor is squared. And if that was a cube on the x plus 2, we just have one more partial fraction where we have an x plus 2 cubed. So a partial fraction for each power of the repeated 0. And then we do the same thing that we've been doing. We're going to do the algebra now. So we're going to take this whole entire fraction, whole entire equation, and multiply it by the denominator on the left. So we're multiplying it by x minus 6 times x plus 2 quantity squared. Entire equation being multiplied by that. So on the left-hand side, we're just left with 16x squared.
Why are you multiplying by all of the denominators?
So we multiply by
just by the, I get it. Yeah.
the left denominator so that it clears. That is the least common denominator. That will wipe out all the denominators.
That makes sense.
So if we multiply it by the left side, it completely wipes out the denominator. And on the right, we're going to have an a over, or not an a over, I'm sorry, a times what?
X plus 2 squared.
X plus 2 squared. X plus 2 squared. Right, this part here is going to cancel with that part. So we're going to be left with just the x plus 2 quantity squared. And when it multiplies to the b, we are going to be left with b multiplied by one of the x plus 2's cancels. So we're going to have an x minus 6 and an x plus 2. Right? When it multiplies by the c fraction, the x plus 2 squared and the x plus 2 squared, those are going to cancel. So we've got that wiping out with that, and we're left with just the x minus 6. So it's going to be plus c times x minus 6. All right, so there is our PFD equation. PFD equation, that's where we can decide whether we go traditional or convenient value. You can also do a combination of convenient value and traditional. Like here you might say, okay, well we have two convenient values for sure, so we could plug those two convenient values in and perhaps get two of our unknowns, and then go to the traditional method to get the third. That's also a hybrid approach is possible. Let's go with convenient values, and I want to show you something. So let's go with convenient values. So there's only two that are truly convenient, and those two are, of course, -2 and 6. So let's start with x equals -2. And then we'll go with x equals 6 next. So when we plug in -2 across the board on the left, we get 64. And then on the right, plugging in -2, gone, gone, -8c. So that tells us that c is equal to -8. Now we plug in 6 across the board. On the left, there's some multiplication I don't want to do right this moment. Hopefully we'll get some simplification. On the right, when 6 goes in, we're going to get 8 squared, which is 64, times a. And then that 6 is going to give us 0 and a 0. So we should be able to solve this for a and get something, let's see, 9?
9, yeah.
So 9 for a. Now we've got two of our unknowns that we found. Now, we could now plug those in. Plug in the c is equal to -8, plug in the a is equal to 9, and start rearranging and combining things and put anything that doesn't have a b in it, we could move it over to the left and set up a whole new equation. So that would be the hybrid approach. But we can also do something different. Instead of a convenient value, we could pick a convenient-ish value. We could pick another value, pick any number we want. Like if we look across here, plugging in 0 would make the left side really simple. All right, that wipes out the left side. So you can plug in any value you want, and so I'm going to pick something that's convenient-ish, and by that I just mean it reduces something. Or maybe you could pick like a -1. If you plugged a -1 in, it would make this a 1, it would make that a 1. That's convenient-ish. It reduces the complexity a little bit. So we'll plug in 0 and see what happens. On the left side, obviously, we get 0. On the right side, when we plug in that 0, we're plugging in 0 for all the x's that we see. So right here, what do we end up with? 4a. When we plug in 0 here, we end up with -12b. Plug in 0 here, we get -6c. And now what we are going to do, we've got that and we've got that. We're just going to plug those into the bottom equation and solve for b. So this equation is going to become 0 equals 4 times a. That's 4 times 9, which is 36. Minus 12b, we don't know b yet. Minus 6c. Minus 6 times c, c is -8, so that's positive 48. Okay, so that's going to be 84, 12b equals 84.
Yep.
And 7. So now we've got all three. So we used our two truly convenient values to get two of the variables, two of the unknowns, the a and the c. And then we just picked some random x value, because this equation is true for every x value. So you could have picked whatever you want, and then you plug those two into that equation, and you get your third unknown.
Does this work for all powers?
You could do this for all powers, yeah. If there's no linear factors, though, you just go traditional method usually.
Okay.
But you could do it with quadratics even.
But if you had an x to the third
Well, you
factor, you'd end up with two things that didn't solve, right? You'd end up with a b and c.
so now we can't get a. So what do you mean by x to the? Do you mean a
Like
linear factor to the third?
A linear
factor to the third.
Yeah, sorry.
Yes.
If you did factor to the
Yes.
third, you'd end up with two unknowns.
Two, yes. So then you could do a second convenient-ish value.
Yeah.
Yeah.
Oh yeah, gotcha. Yeah, you
Right.
just have one of them.
Then you're gonna, yeah. So you could do it. You still could do that. So what do we have then? Let's see. So now all we've done so far is rewritten that. So let's take our original integral and let's rewrite it. So we'll call the original integral something just so we can reference it. All right, so the original integral is now going to be equal to the integral of, so we said that a is 9, so it's going to be 9 over x minus 6. 9 over x minus 6. And then b is 7, so plus 7 divided by
X plus 2.
x plus 2. And then
Minus 8.
minus 8 divided by
X plus 2 squared.
x plus 2. Oh yeah, that was the repeated one, dx. So there we have a way simpler integrand. The first two are obvious. The third one should be obvious, but maybe it isn't. Think about that third one while we write out the first two obvious ones. So these are both logs. Absolute x plus 2. And I'm going to rewrite the third one in hopes that it becomes obvious, if it's not obvious yet. So if we have an x plus 2 in the denominator with the power of 2, we can bump it up to the numerator, and we can just do power rule. Right? We have a linear expression raised to a power. Just use the power rule. If this happened to be something more complicated than x, like if it was a 4x, then we'd also have to do reverse chain rule. Have to divide by 4 if it was a 4. But that's all we have to do. And you can kind of see here, you can kind of see now why we're not going to always combine the logs into one, because now we have powers of 9, powers of 7. It just gets tedious. So usually when these coefficients get larger, we usually just leave it in log form. Okay, so we add 1 to this exponent, getting a -1. Divide by that new exponent, so we're dividing by -1, which is going to turn this into a +8. So we're going to have x plus 2 to the -1 divided by that -1. And then if we had to do reverse chain rule, we'd divide by that coefficient, plus c. So there is our answer. That is our final answer there. All right, any questions on that whole business?
I probably
Yep, go ahead.
probably missed it, but when you put the integral with x plus 2 and you put it to the -2, let's see how.
So this power is positive 2 in the denominator.
Okay.
So we can always move factors up and down, and if we move a factor up or down, it changes whatever the sign is on that exponent. So if we move it up to the top, so if we think about integrating something, like if we just had something a little more simple, if we had like dx divided by x cubed, our strategy would be to pull that into the numerator, which would change the sign. And then we could go with our power rule, and this would be x to the -2 divided by -2 plus c.
Perfect. Thank you.
Does that make sense?
Yes.
And now on this one here, you could rewrite this and put it as 8 over x plus 2 if you wanted. And you can move it back into the denominator. Okay, so now it's recognizing my finger as a scroller. So let's set this one up, and then we'll take our break, and then we'll come back and finish it. Let's just get it set up before we go off and take a little break. So we're going to take the inside here and rewrite it. So first off, I'm hoping that when you see that denominator, you're seeing it as a repeated linear factor. And that's a repeated linear factor. And this is going to be split then into a partial fraction for each power of that repeated linear factor. So that's going to be what our next step is, the form of our PFD. And then we multiply the entire equation by the denominator on the left. And let's notice what we're left with. So we will be left with, on the left, just x squared, just the numerator. On the right, a multiplied by x minus 2 quantity squared. Because one of the x minus 2's will cancel. And then we multiply it by the b fraction. And 2 of them cancel, and then we multiply it by the c fraction, and they all cancel. Yes. Okay. What is the only true convenient value? 2. So let's go ahead and take advantage of that convenient value. And this time we'll do it with the hybrid approach, so you can kind of see how that looks in practice. All right, so we're going to plug in x equals 2 all across wherever we see an x. So we're going to make that 4 on the left. Oh, done. That was easy enough. We got C. C is 4. Okay, so let's keep going a little bit. We still have some time. So what we're going to do now, so the way this hybrid approach works is that we are now going to substitute that value back into the equation and rewrite the equation. So when we plug that back in, we have this. And if we're going to do a true hybrid approach, that means go to traditional method now. We would multiply this all out. So this is going to be x squared minus 4x plus 4 plus bx minus 2b plus 4. And so what we would want to do is move the 4 to the left, because there's no unknown with that 4, so we're going to move it to the left. And then on the right, we are going to group together all the like terms. So there's only one square term. And then the linear term is going to be minus 4ax. And then a 4a. And here's where you can get really, into the minutia. You could, pair, you can take these two terms and factor out the x, and you can get really detailed. But if we see that those are the linear terms, we don't really have to go any further. There's the quadratic term, and then this is the constant term here and here. So let's set up our system. So our system says, let's use that color, I guess. What is the coefficient of x squared on the left? 1. Coefficient of x squared on the right? A. So we have A. What is the coefficient of x on the left?
0.
0, right? X squared minus 0x or plus 0x. And now if we look on the right, the coefficient of x, negative 4a plus b. So we're going to take the two x terms and grab their coefficients. So negative 4a plus b. What is the constant on the left?
Negative 4.
The negative 4. Constant on the right?
4a minus 2b.
4a minus 2b. We grab everything that has no x in it. So 4a minus 2b. And so now we're sort of back in the traditional method where we have to solve this system. And it's pretty easy because we already know that a is 1 and c is 4. So it's going to be pretty quick. So if a is 1, come in here. Oh, we didn't even need the last equation, did we? Yeah, so it's redundant. Doesn't matter which one we plug it in. If we plug in the 1 right there, we're going to see that b is equal to 4.
And if you do it for the last one as well.
And if we plugged it into the last one, we better get the same thing.
Yeah.
Okay, so let's go ahead and take our break now, and then we'll do the integration after we get back from break. Integrate.
That's a lot.
The method to the madness here, when we have those powers in the denominator, we can just bump them up to the numerator and use the power rule, right? So the first one, no need for that because the first one is in log form. So we'll get natural log absolute x minus 2. So that's the only one you can't use the power rule for, because if you added 1 to its exponent, you would divide by 0. So you can't do that. So the log form we have to do separately. But then these ones here, let's rewrite them first. So that'll be 4 times integral x minus 2 to the negative 2 dx. We'll just separate them out into two separate integrals. So everybody's seeing that step? And then we just do our power rule part. So the power rule says add 1 to the exponent, divide by the new exponent. So let's be careful here. So when we add 1 to that exponent, we get negative 1. Dividing by that negative 1 is going to make this thing a negative out in front. And so we'll have that plus, add 1 to that exponent, we get a negative 2. Divide by negative 2, we're going to get what out in front?
Negative 2.
Negative 2. Come on, go away. There we go. So we've got that. He's already bored.
Yeah, no, I already got it wrong, so I'm gonna give up and switch
So you
to
go
art.
back to Calc 1?
Yeah, I gotta go restart. Thank you for having me. You guys have a good one.
So if we wanted to, we could. One other thing we could do is, just rewrite this. You don't have to, but if you wanted to write this in this form, usually we like to get rid of negative exponents. Is it necessary to get rid of them? Not necessary, but usually the preferred answer has no negative exponents.
How'd you get that negative 2 out front of exponential?
This one right here?
Yeah.
So when we use the power rule, we are adding 1 to the exponent.
Negative 2.
So we're adding 1 and getting negative 2 right there. And then we have to divide by that new exponent.
Yeah.
So we get a negative 2, and that negative 2 divides into 4, giving negative 2. So dividing by the new exponent. Any question? Zach, question?
What is he doing here?
Harassing us. Harassing us. Nothing more. Nothing useful.
Is it?
That's it, just harassing us.
Mildly distracting.
Yeah.
Does he know anyone or?
These two.
Imagine he's just like some
You
random
also?
guy.
They all play Magic together.
Oh.
But you guys went to, you guys go to like elementary school together or something?
Centaurus High School.
High school. High school.
You guys play 40 Commander? Or... Dope.
I'm bringing the commander deck next week.
We got some magic happening. Okay, so the last case. So we only have 3 cases. We have a linear factor. We have a linear factor that has a multiplicity. And now we have an irreducible quadratic factor. So remember, an irreducible quadratic is a quadratic that can't be factored with real numbers. You have to use imaginaries. So the classic irreducible quadratic is x squared plus 1. It's a sum of squares. X squared plus 1, x squared plus 4, x squared plus 9. None of those can be factored without imaginaries. Right? X squared plus 1 is x minus I, and x plus I, we don't want i's. No i's. So here is the one major difference. Notice the numerator. With our linear factors, the numerator is a constant. With our irreducible quadratic factors, our numerator is going to be linear. We basically want to create a proper fraction. If the bottom is a power of 2, we're going to create the largest possible proper fraction so the numerator can be a power of 1. When we had the denominator being linear, the numerator had to be a constant to keep it a proper fraction. All right, so when we look here at this first example, we're going to take the inside and we're going to rewrite it. And notice that we have one linear factor. So that x, that's a linear factor, x minus 0, linear factor. And the other factor is an irreducible quadratic. Is there a quick way you could tell if something's an irreducible quadratic? Of course there is, but what is it? Say again? If you can't factor, if it, just because you can't factor it, maybe Robert can, so there's a surefire test.
A number is either always negative or always positive.
You could look at that it never meets the x-axis. And there's a quick way to test this. If you take a look at the discriminant, b squared minus 4ac, quadratic formula, the discriminant, b squared minus 4ac, if the discriminant is negative, you know you're going to get imaginaries. So if you're not 100% sure, you could always just look at the discriminant. So b squared minus 4ac is the discriminant. B is 2 here, so 4 minus 4, and then a is 1, and c is 2, so you're going to get negative 4. If that's negative, then you know it's an irreducible quadratic. You know that you're going to have 2 imaginary zeros. Because if you were to do the square root of b squared minus 4ac and get a negative, you're going to get i's. So that's how you could know for sure. Okay, so this tells us that we do have one linear factor and one irreducible quadratic factor. So there's our linear factor. A divided by x will be the fraction associated with that linear factor. And then for the irreducible quadratic, we're going to have bx plus c over that irreducible quadratic factor. So we've got that. So that is the setup. And if you had a repeated irreducible quadratic, we do the same thing that we did with the repeated linear. You have an extra fraction with that extra power. So if this here had a power of 2, we would then have to have another partial fraction where that thing is raised to the second power. So if we had a repeated irreducible quadratic, you would just have an extra fraction. Yeah?
So that bx plus c, that's just 3x plus 2?
No, not yet. No, because so we don't know, these 3 unknowns are still unknown. We don't know what those might be, and they are very likely not those, most likely not. We'll find out real fast. When we multiply by the denominator here, let's see. So we're going to multiply both sides by the denominator on the left. And when we multiply by that denominator, the x's cancel here, so we're going to get a times that irreducible quadratic. And then over here, when that denominator is multiplied by this, the irreducible quadratic factor cancels, and we have bx plus c multiplied by x. We have that. Is everybody clear on that step? So we're doing the same thing we did before. We're taking the whole equation and multiplying it by the left-hand denominator. Everyone see that? And so now now we have our PFD equation right on time, Edgar. Better late than never. So now we have our PFD equation, and we want to ask ourselves, should we do convenient value, or should we do traditional, or should we do hybrid?
Hybrid all the way.
We could do hybrid because we have one convenient value of 0, so we could definitely do that. So let's go for it. Let's do a hybrid approach this time. So we know that x equals 0 is a convenient value. And when we plug in the x equals 0 on the left, we get 2. When we plug in x equals 0 on the right, we get 2a. So we get that a is 1. Everyone see that? If we plug in the 0 on the right-hand side, this whole piece goes away. Those two terms go away if you plug in 0. So all we're left with is 2a. Divide by that 2, and we get our a value. Okay, so now the hybrid approach, we take the a, plug it in, and reshuffle. And by reshuffle, we mean anything that doesn't have an a, b, or c, anything that doesn't have one of those unknowns goes to the left side where there's no a, b's, and c's. So let's do that. So now we're reshuffling. So we have the left side. Now we're plugging a equals 1. So if we plug in a equals 1, we get this. And then we still have this stuff over here. We can multiply this out now since we're switching to the traditional method where it's better to have everything multiplied out. Now this reshuffling, anything that doesn't have an unknown, a b or a c, we already got rid of a, so no b's and c's, those can be combined over here. These are now like, right? Those are like. The x squareds cancel. The 2's cancel also. And 2 of the x's, so we're left with what, just x? So we have this. So everybody follow what we did? So as soon as we plug in that a equals 1, now we have like terms with the left-hand side. Right? There's no a here anymore, so those can be combined with the left-hand side. Subtract off the x squared, subtract off the 2, subtract off 2x. And this immediately tells us that b is equal to what? B is going to be equal to 0. Because on the left-hand side, we have 0x squared. Right? So the coefficient of x squareds have to match. So this tells us that b equals 0 and c equals 1. So we've got both of those two right away. Coefficient of x is 1, coefficient of x squared is 0. So that is the hybrid model. That's a good example of using hybrid. All right, so now we are ready to, we need a little more space here. So plug and chug with our integration. So the original integral, call it whatever you want. We're going to have the integral of a, which we said was 1. So a is 1, and that's divided by x. Whoa. So that is divided by x. So 1 over x. And now we have our irreducible quadratic term. And let's see, we found b to be 0, so it's going to be 0x plus c. So 1 divided by, oh, come on. 1 divided by
X squared plus 2x plus 2.
That. Right, so the first one is a log, no problem. Piece of cake. We like that one. Second one, we've got a trinomial downstairs. So, can we factor that trinomial?
No, that's
You
why
already
we
proved
got
that.
it.
We can't factor it?
That's how we got it, right?
Is that the same trinomial?
Yeah.
Well, that's the irreducible fraction, or irreducible.
Yeah.
Oh yeah, yeah, it's the same.
That's why it's there.
Yeah, so we can't factor it, right? That's why it's there. We can't factor it, right? We would have factored it originally. So what do we do with that one then?
Complete the square trig set.
Yes. We complete the square.
Yeah.
Complete the square. Yep.
One, right? Plus.
Okay, so we get natural log, absolute value of x, and then we are going to complete the square. So we need a 1, right? So we're going to make it x plus 1 squared plus 1 dx. So if we divide that by 2 and square it, we get a 1. So we're taking away 1, 1 from the 2.
And we can skip to do the inverse tangent.
Inverse tangent, it's in inverse tangent form right away. So we don't have to do any trig sub. So we'll have natural log, absolute x, that's inverse tangent of whatever's in parentheses plus c. And we don't have to do any reverse chain rule because it's x plus 1. It's not 3x plus 1. If it was 3x plus 1, we would divide by 3. Yeah. Okay, so you all give this one a shot. We have 2 irreducible quadratics. If you want to switch to x's, you can switch to x's. So 2 irreducible quadratics. So first, go ahead and write down your PFD form and then see if you can get it. Yeah. Yeah. Trying to write math digitally can be hard. So that is the form of your decomp. So now see if you can find A, B, C, and D. Oh boy. Is that a 5-year CD that you're talking about?
So 60 months. You can get someone up by 5%.
Wow. They've been low for so long. Other than the I bond. So there's step 2 up there. After you've multiplied both sides by that denominator on the left. So that gives you your PFD equation. So you multiply by that common denominator on the left, right? There's your PFD equation. And now with an irreducible, that's got to be in parentheses. Those do, yeah, because if those aren't in parentheses, then only the D, then, yeah, so that implies you have to FOIL it all out. So when both are irreducible quadratics, we definitely do not want to use the convenient value method. There are no convenient values. So the only thing we can do is FOIL it all out. So we've got to multiply it all out. So FOIL away. Let's see if you can do some algebra. FOIL.
You're asking a lot.
I know. It's a Thursday. You get to have a break later. So no choice here, you've got to FOIL it out. There's the foiling. Hopefully that's the thing I got. Foiling all that mess together. First outer inner last, all that stuff. So here, the PFD equation, we've expanded it. Now the traditional method says on the left you have a polynomial, on the right you have a polynomial. The only way those two polynomials can be equal is if the powers match. So let's set up our power equations. So our power equations, if we look on the left, what is the coefficient of y cubed? 0. And on the right-hand side, we have as the coefficient of y cubed, a plus c. Exactly. So there are the cubes. Now let's go with the squares. So the squares, powers of 2. Let's see, on the left, the power of 2 is 0. And then on the right, the power of 2 is b plus d. Now we go to the linear term. The linear term on the left has a power of 0. And on the right, the linear is 2a plus c. And then we go to constant. The constant on the left, 1. The constant on the right, 2b plus d. So there is our system of equations that we have to solve for a, b, c, and d. Clearly, we are going to pair these two. If you use the elimination method instead of substitution, you can do it right away. We could subtract the top of the equation 1 from equation 3 or vice versa, it doesn't matter. So if we subtract the two, if we do 0 minus 0, we get 0. 0 minus 0. 2a minus 1a is 1a. C minus c, 0. So if a is 0, c is also 0, so we've got 2 of them done. And then let's go to these two equations. Same idea, if we subtract, the d's will just go away because we have one d in each. So let's do bottom minus top. So 1 minus 0 is 1. 2b minus b is b. d minus d is 0, so b is 1.
And then b plus d is 0.
So b plus d is 0, so d is negative 1. There we go. So now we have all four. All right, any questions on solving that system? Yeah.
Will A and C always go to 0 if it's a constant above the quadrant? If it's, since this was specifically dy, if it's just a constant on top, will it always go to 0?
I think that is actually true because these two, when we multiply, actually, I don't know.
Yeah, I can it feels like it should.
I think it depends.
Might depend on-
Because we are going to have to multiply this by that and that by that. I don't think that's
Actually, it might
always true.
depend on if the bottom has a y factor as well. I guess if it had a linear factor, it might have multiplied out in a weird way.
Yeah,
It would have
yeah.
made that not true.
Yeah, I don't think we could conclude that.
Yeah, I'm crazy. We're good.
That's all. Crazy's good.
Pretty smart.
Crazy. All right, so let's call that omega. And then let's go ahead and set up our new integral. So omega will be equal to the integral. So the first one was ax or ay plus b. So we just have b over, was that one y squared plus 1? And then plus -1, so we'll make it -1 over y squared plus 2
Yeah.
dy. Pretty cool looking.
Actually, that's interesting.
What's the first one?
Trig, the tan thingy.
Yeah, that. Inverse tan of y. Yeah. I'm with you. I'm hearing you. Inverse tangent of y. Inverse tangent of y. Now the second one, we have to be a little more careful. We see a sum of squares, so we definitely are thinking inverse tan. But we have been
Don't see it.
approaching these by doing a factorization so that we have a sum of squares with a 1. So I'm going to factor out the 2. So factoring out the 2 that's in the denominator, factoring out that 2. And there is no 2 with this y squared. So it introduces a 2 in the denominator. So we're going to factor out that leading 2 right there. And so how can that denominator be rewritten then?
Y
Y
over 2 squared? It's probably the same thing, I think.
I think I heard it right.
Y over root 2.
Y over root 2 squared? All right, so we're left with this part right here. We're left with the y squared over 2. And we want to write y squared over 2 as a single square. So we have to make that denominator a root 2. And now it is definitely in the form that we want it in for inverse tangent. So it's -1/2. I'm going to leave a little bit of space here for a reverse chain rule, because I see that it's not just y, right? It's a constant multiplied by y, so we're going to have to do reverse chain rule. So now we're going to have inverse tangent of whatever's in the parentheses. So y divided by the square root of 2. What is the derivative of this quantity?
1 over square root 2.
1 over square root of 2. Dividing by 1 over square root of 2 means multiplying by the reciprocal, so that means multiplying by square root of 2. Let's see. And we could combine this and make that a root 2 over 2, but that's about it. Uh-oh. Oh, did it? All right, questions on any of those steps? Those inverse tangent integrals are going to be all over the place, so definitely want to practice those ones. They're always around. All right. Now the next section that we're going to cover on Tuesday, improper integration, That is the did I say it right? Improper integration. That is the second hardest topic in this chapter. So there's trig sub and then improper integration. And it is really helpful to read ahead before we get to improper integration because it's complicated. You know, not as complicated as trig sub, but it's definitely not as easy as a procedural section like this. So read ahead before we get to improper integration. Okay, let's do that. So we want to find the area of this region. That's a curve you should definitely be able to graph really easily. Not. That is a graph that you would be given. Okay, so see if you can find the area of that graph from 0 to 1, area of that shaded region. A concocted application. Now they've already factored that denominator for us, keep that in mind. So a lot of times you're looking at an unfactored denominator, and if you can factor it, you go to PFD. Here they've already factored it, so we kind of know, oh, we're going to do PFD. Denominator is factored.
You set one side equal to the other side. You want to have the coefficients of x squared and x next to 0 and whatnot. So you want those to be. You want them to be distributed. So it's like,
So we've got one linear and one irreducible quadratic. The numerator on the linear is a constant. The numerator on the irreducible quadratic is linear.
No, they just upgraded the floor cleaner.
Finally?
Oh. You should say that now.
So denominator, if the denominator is linear, then the numerator is constant. If denominator is an irreducible quadratic, then the numerator is linear.
that's incredibly helpful. I just got to the equation that -1 equals -1.
No solution.
Certainly is true.
works.
That certainly is true.
My brain skipped over dx because it was
So zero.
Otherwise, if you had two linears, then it would just be A, right?
Yeah. So if it was just x
Yeah. Cruising. Cruising.
plus c plus
When you get to that PFD equation, you have your choices. You can just do all traditional, you could do hybrid and
x squared goes with the
do one convenient value.
a. A is x cubed. So x cubed is now x cubed, so it equals 0. There's not a cube.
It's not ax over something.
It's just a. Yeah, because
It's not ax plus b over linear. It's only
yes,
ax plus b
a squared is
over.
with the a, right?
What Julian has is ax plus b over x plus 1,
So then if you plug
which
in
has an extra x.
So it looks like a lot of you are doing it one convenient value, which makes perfect sense. So the one convenient value is the x value that makes this 0. So that convenient value is x equals -1. So x equals -1, we plug across the board. So -1 minus 1 is -2. -1 here gives 2a. -1 here gives 0. So a should be -1.
A is -1, okay, that's what I got, thank God.
So once you get that linear 0 worked out like that, now we have to reshuffle the equation. So we reshuffle it by plugging in that -1 for a, combining like terms, and then doing the coefficient match strategy. So when we reshuffle, -1 is going in here for a, so that's -x squared minus 1. And then we should FOIL out this other stuff on the end. So as soon as we find one of those unknowns, plug it back into the PFD equation. Now we want to combine like terms here. These have no unknowns in them anymore. So we want to move them to the other side. So it looks like the x squareds are going to cancel. And on the left, we're going to end up with just x plus 1. And on the right, we have all this stuff with the b's and the c's. Now we're going to do our coefficient matching setup. What is the coefficient of x squared on the left?
0.
0. Coefficient of x squared on the right is b. And then we're going to go to the linears. Linear on the left is 1. Linear on the right is b plus c,
Which is 0 plus c.
which is 0 plus c. And c is 1. Whoops. We have 1 on the left for the constant, 1 on the right, c on the right. Yeah, oh yeah, we already had c is 1 anyway. Yeah, we're done there. So everything is done. So c is 1, b is 0, and a is -1. All right, so now we can rewrite this integral so that we have, let's come over here. So -1 divided by x plus 1. And then we had bx plus c,
b is 0.
so 0x, so just a 1. Oh, that simplifies pretty nicely, actually. Both of those are easily integrable.
Hopefully.
So we get -1 natural log, so minus natural log absolute x plus 1 plus arctan of x. And this is all going from 0 to 1.
Oh wait, not plus C.
Plug in the 1, we'll get negative natural log of 2 plus arctan of 1, which is angle on the right with the tangent of 1, pi over 4. Angle on the right with the tangent of 1, pi over 4. Now we plug in 0. Plugging in 0 here, we get ln1, which is natural log of 1 is 0. Arctan of 0 is also 0. So there is our final answer right there. That'll be our area. Okay, any step you want to ask about? All right, let me ask you a question. Let's suppose, why does it stick it way down there now? Used to stick if you added a new page, you used to stick it right below where you were. Which makes more sense.
You have to use your finger for the select when you're using the pen.
Oh, that's,
It's registering as the pen.
even if I'm doing that, even if I have that.
Yeah.
Yep, that makes sense. So I could just move it like that.
Theoretically.
Theoretically.
You have to hold for a second.
Theoretically.
There you go. Now you should be able to. I
Now
stand
you can
corrected.
right
It's a,
You've discovered how
these
to
boards are just funky.
Yeah.
Okay, let me ask you this question. What if, so let's suppose we have the integral of, or let's not even go with an integral, let's just do the PFD piece. So let's suppose we have x plus 5 divided by x cubed times x squared plus 1 squared. Let's just write out the setup for the PFD. We won't go through it because it would be too long. But I want to make sure you have the setup right. When you're seeing that x cubed, you should be seeing that as a linear factor that's got a 3 multiplicity. So you should, and it's not a bad idea to write it, oh my gosh, the white paper's so bright. You could write this as x minus 0 cubed if you wanted. I gotta change that paper, that's way too bright. So go ahead and start writing out that PFD for that thing.
That's
Which
terrible.
background?
Yeah, I'm just gonna change this over to nice, easy gray.
And they should have white text on black.
Yeah. You could do that.
Except that none of the preset pens is white for some reason. I presume you can change them, but
Invert.
We can use yellow. Yellow,
Yellow on black's nice.
Standard. Approximately.
any bright color will work.
So here is what your PFD should look like.
somebody.
So we want to have a fraction for each power of each factor. So the x has a power of 3, that's a linear factor cubed, so we need to have a fraction for each power of x. Now for our irreducible quadratics, these are irreducible quadratics, we're going to have a dx plus e over the irreducible quadratic to the first power,
And for the second one.
and then an fx plus g over the irreducible quadratic factor squared. Terrible. That's why we're just setting it up. Just setting it up. That makes sense?
Yeah, you get like a 20 term.
Yeah, it's gonna be brutal.
20 term.
Now, let me show you one thing. Let's just suppose we have something similar. Suppose we have something that looks like this. Let's suppose we have x squared times x squared plus 4. Let's just do that. So the first thing you should be seeing is that this is a linear factor that's squared. Right? So a linear factor that's squared, your setup, based on what we've all been doing, is a over x plus b over x squared, right? And then we would have cx plus d divided by x squared plus 4. Everyone okay with that? Notice that you could, sometimes people will look at that square and say, oh, it's a quadratic. Let's make that instead, let's do ax plus b over something, right? But that is not an irreducible quadratic. This is a repeated linear factor. That's not an irreducible quadratic. Everyone agree? So you just have to be careful. Because if you did do like ax plus b, if you multiplied this by x over x, you would end up with that. Which actually is what you would put on top of x squared if you were treating it like an irreducible quadratic. So the one case where you have powers of x, if you do just have a square, you actually could you could sort of mistakenly interpret it as an irreducible quadratic and it would be okay. But if you have a cube or anything else, you definitely, it's not going to work if you somehow treated that as irreducible.
Isn't it? The thing is, in at least in my eyes, it's kind of obvious it's reducible. X times X times
Yeah,
X.
exactly.
It's really obvious.
Yes, and so if you don't see that, then you could make this mistake and just go right to there, but it actually is not going to matter because it's going to turn out the same anyway. But only if it's a square.
But wouldn't it also work for the one you just did with x cubed? Because it would end up being x squared plus bx plus c over x cubed, right? Isn't that what you would do, is take the highest power of the highest
Highest power of the single
proper
factor.
fraction, basically. Highest power.
Yeah, because that would end up being ax squared plus bx plus c.
So as long as you go
Yeah,
all the way
yeah.
up to
If you
the
look
x
up to the
value,
highest power.
up to the highest value you
Yeah.
actually can,
That
it'll
could
still work out.
still work out.
It's
Yep.
just that this is easier to remember
Yeah, exactly. So yeah, that's true. You could.
than trying to add terms to your thing, not necessarily. But
But, yeah.
theoretically, it could work.
Okay, so just wanted to point that out. All right, let's take a look at the volume of a solid here. So we've got the volume that's going to be created by rotating this region, this shaded region around the x-axis. Now, whenever possible, so we know that we could use disks, washers, or shells. We are going around the x-axis, so this is our axis of rotation right here. The shell method will not work here because it's not horizontally simple. So for a shell method, you have to have parallel to the axis. And we can't, if we try to draw, a horizontal line there, we're whacking the curve. It'd be a pain in the neck. So yeah, we'd have to break it into two and it would be a nightmare. So we're
Also,
going
you have nice bounds in the other direction. You have nice bounds for x.
to, we have great X bounds
You have
also.
gross
What
y
about
bounds.
shell
That's-
method?
Well, that's why we just said we don't want to use the shell method because the shell method would be a horizontal integration element. So we're going to use a vertical integration element because that'll create a disk. And a disk is going to be the easiest way. If we rotate that around, we're going to get a disk. So that's going to be the way to go, is with a disk. So we are going disks, and the area of a disk is pi r squared. So the area will be pi times the radius squared, and the function is the radius. Right, the function, that distance right there is the function. So we're going to have pi multiplied by that squared, which is going to get rid of the square root, which is going to make it a lot simpler. So we're going to end up with pi divided by 4 minus x squared. So that is the area of a disk at x. Those dots didn't do the disk justice. So then to get the volume, we integrate the area. So integrating area to get volume. And if we want, we could use some symmetry here. When this shape is rotated around the x-axis, it's going to create a symmetric left and right shape. So we could go 0 to 1 and double it. Everyone see that? You could also go -1 to +1. If you can avoid negative numbers, it's a good thing. If you can use 0, it's a good thing. So now we are in the section with PFD, partial fraction decomposition. You could do this with trigonometric substitution also. You have a difference of squares. But let's go PFD. Now when we go PFD, first off, let's factor out the pi. Let's also factor out a -1. And we're going to factor out a -1 from that denominator so that we get the polynomial in the denominator in descending order. It's always easier to factor when we have a polynomial in descending order. So this is going to be our factored denominator. We'll factor that difference of squares into x minus 2 and x plus 2. So then we can do PFD on the integrand there. So we're going to take the integrand linear, both factors are linear. That's the best case scenario. When both factors are linear, we can do an a over x minus 2 and a b over x plus 2. So that's the simplest case. So a divided by x minus 2 plus b divided by x. That. And then we multiply both sides by the left's denominator. So we get that. Clearly, we're going to use convenient values because both are linear. Convenient values work really well for linear factors. What's the first convenient value?
2.
2 and -2, either order, yep. So those are our convenient values. If we plug in -2 across the board, we get that b is equal to -1/4. If we plug in 2 across the board, we get 1 is equal to 4a. So a is 1/4. That allows us to rewrite the integral. Well, let's see. I'm going to factor out 1/4 so that we don't have a fraction inside the integral. So factoring out 1/4, that 1/4 factors out as a 4 in the denominator. And so for A, we have 1 over x minus 2 minus 1 over x plus 2. So that'll be our nice simplified integral using PFD. So that reduces to negative pi over 2, quantity, natural log absolute value x minus 2 minus natural log absolute value x plus 2 on the interval 0 to 1. Let's So now we substitute. So negative pi over 2. Plug in 1. When we plug in 1, we are going to get natural log absolute value of negative 1 minus natural log absolute value of 3 minus natural log absolute value of negative 2 minus a minus, which is plus natural log of absolute value of 2.
And natural log absolute negative 2 is just the same thing as natural log of 2, right?
So this one's going to be 0. Natural log absolute 1 is that's natural log of 1, which is 0. These two are also the same. These are just going to cancel.
Yeah.
We have natural log of 2 minus natural log of 2. So those cancel. So we end up with positive. So pi times natural log of 3, don't need an absolute value, all divided by 2. Yeah. Snazzy.
Units cubed.
Questions, Zach?
Raise I will have on the homework, but
Just stretching.
I will have a question on homework.
Mm.
Just in a few minutes.
But you don't know it yet.
Just stretching right now for this one.
So let's see, so if I add that page, can I get it with my finger? No, I can't.
Wait, when you hold down on it, I think the
Hey, it worked.
popped up for a second.
You just drag
Nope, that's a right click.
up from the edge. Just drag up.
Oh, there it's going. Okay, all right, from the left, that works great. Don't touch the title of it.
Yeah.
Get the,
I think the title wants to rename it.
yeah, title once. Okay, so let's take a look at the,
It's night mode.
that's a little lighter gray. That's okay, better than white. So let's do, I want to make sure, we've done so many inverse tangents. Let's do, I want to make sure this one doesn't get, come on. Let's do another one of these. So, not PFD, let's go back to trig sub. Trig sub is something that you can never do too many examples of trig sub. So first thing we see, a difference of squares. As soon as you see a difference or sum of squares, trig sub is a viable technique. Now we always like to have a sum or difference of squares with a 1. So I'm going to factor that 4 out. What comes out in the denominator if we factor that 4 out?
4 over 4. I'm sorry, 1 over 4 over 4.
So that 4 is coming out in the bottom. Square root of 4 is 2. 2 cubed is 8. So it's coming out as a 1/8. Right? This 4 has to have this power come with it. Square root of 4 is 2. 2 cubed is 8. So now we have a 1 there. There was no 4 here, but now a 4 appears in the bottom, so we write it as x over 2 quantity squared. And that's all to the 3 halves.
And then was the leading one its sine?
Yep, so we have a difference of squares with a leading one, so we're gonna go with sine. So we are gonna say that x halves is equal to sine of theta. And then we take our derivative. So there's the derivative. And then our substitution back in is going to look like this. dx is 2 cosine of theta d theta. And then down below we have 1 minus sine squared. 1 minus sine squared is cosine squared. And that's all raised to the 3/2 power. So we're going to end up with 1/4 out in front, integral. How many cosines do we end up with down below?
3.
And there's 1 up above, so we're going to end up with 1 over cosine squared.
Yeah.
Bless you. And then we can turn that into secants. And what's the integral of secant squared? Integral of secant squared.
Oh, it's a secant tangent.
No,
No.
Tangent.
Just hand it.
Just tangent. So easy to get tangled. Okay. All right. Now we want to get back to our x's, so we need our magic triangle. So our triangle, always put theta in the bottom left. Sine of theta is x over 2. Sine is opposite over hypotenuse. The missing side is found by Pythagorean theorem. Tangent is rise over run. So x divided by square root of 4 minus x squared plus c. Little inverse. Little trig sub. Question?
If you do like 2 lines up, yeah, in the denominator, what all happened there?
So our substitution is sine. So this is sine squared right here. So 1 minus sine squared is cosine squared.
No, I mean to the next step.
Yeah, and then when you have a power to a power, you multiply. So 3 over 2 times 2 over 1 is 3. And then one of them cancels with the numerator.
Cosine over cosine cubed. 1 over cosine squared.
So this whole denominator is a cosine cubed. That denominator is cosine cubed. And then one of them cancels, giving cosine squared.
And the 2 gets
So 3/2 times 2 is 3, and then 1 cancels, leaving 2 in the bottom. You seen it? Stare at it for a minute. Okay, see you all on Tuesday. Have a great. I'll see you or in the Math Center. Or in the Math Center. Do you see it yet, Dustin?
No.
So, do you agree with this one here?
Yeah.
That one you agree with?
Yeah.
So let's just take away all the extra stuff. So we have c over c squared raised to the 3/2. And so that's c over, you multiply these two together. So 2 over 1 times 3 over 2, those 2's cancel and you get c to the 3.
Yeah.
So then 1c cancels and you're left with 1 over c squared. See it? Did it make its way through the blood-brain barrier?
And that's
Yeah,
why
like
it was
way
d
out of
theta over
Yeah,
squared over there, right? That's where we're at now?
Yes. So this 2 over 8 becomes the 1/4. And that 1 cosine is going to cancel, leaving just a cosine squared down below.
Okay.
And then cosine squared in the bottom is the secant squared at the top, and integral of secant squared.
It seems so much simpler.
Right?
To just do the
Totally.
first letter.
If you have just sines and cosines, just doing the first letter is really,
I
really
need to
easy.
practice that.
If you have just sines and cosines,
Voila.
voila!
I love dark mode, but
Yeah.
that's just me.
I know, I love it too. I love it too. I love it too. You know, and maybe it is easier to see maybe from the sides.
I personally find it easier to see.
Oh, yeah.
That's just me.
No, maybe that's not a bad idea.
It's neat that it actually converts all the colors too. I didn't realize it would do the colors.
Yeah, so it automatically turns the black to
so when
that.
you go back to your draw, black becomes white automatically.
Oh, it does.
Yeah, so you're drawing with blue, so it just inverts the
Oh,
value.
yeah, okay, so that, okay.
Switch it.
Then when it's switched, then, okay, all right.
And the YouTube is just, the video that you're doing is just recording the screen, right? So we're
Yep.
dark mode as well.
Yeah.
Oh, yeah, to be in dark mode on the video.
Yeah, well, just
Now.
Yeah.
Yeah, currently.
Currently,
And this top.
and if we go back here,
It automatically switches.
As
all
long
the-
as you're in
automatic-
dark mode, it doesn't.
yeah, it's gonna switch, okay. Yeah, that's a good idea. Yeah, we should do that.
It looks like the highlighting shows up kind of poorly on it. So if you go back to
The
that one,
highlighting might,
No, highlighting works great.
well,
I love it. I'm biased.
let's see. It's certainly
I see
different.
it, but yeah, it doesn't change the color of the highlight.
Oh, pink doesn't work so well on it.
If you're not drawing currently, use your finger.
Oh, it was working when you was drawing.
Yeah, I was just drawing on this one with my finger.
I don't know, but just the paint just.
Pink just seems to,
Huh?
why does pink vanish?
That's
I
it.
think when I saw it on the white
Okay.
one, if you go back to the volumes page, I think. Yeah.
Huh. Just change the color. Doesn't need to be pink.
Yeah, exactly. Yeah,
And then what's this, a laser pointer?
yeah, it just disappears. So do that and then it vanishes.
Oh,
That's Andy.
I like it.
Vanish. Oh, let me just pause the video. Yeah, dark mode. Yeah, maybe dark mode might be. I'll play around with the highlighters and see if there's.
Yeah, because I saw on